In this video, we give an example to show how to build an optimization model. Assume we are asking a painter to paint the MC building in 3 days. The work has to be done from Saturday to Monday. First, how much do we have to pay him? The standard rate is $20 per hour. However, if it is Saturday or Sunday, then we have to pay him at a higher rate. For example, $30 per hour for working on Saturday, and 40 hours for working on Sunday. Secondly, the painter doesn't work at the same speed. For example, he's working slower on Saturday. This means if we pay him to work for 10 hours, then he will be only working for 9 hours effectively. In total, we need 20 hours to finish the job, and the painter can work at most 10 hours a day. So the question is, how should we schedule the work for the painter so that the cost is minimized? We can create a mathematical program to solve the problem in the following way. Let x1, x2, and x3 be the hours worked on Saturday, Sunday, and Monday, respectively. And we want to minimize what the painter is paid. On Saturday, we pay him $30 per hour. So on Monday, we pay him 30 times x1. So similarly, it's 40 times x2 and 20 times x3. We also need to add the following constraints. On Saturday, he is working slower, so it's 0.9 times x1 plus on Sunday is x2 at full speed plus 0.7 times x3 on Monday, and this has to be equal to 20 hours. Since the painter can work at most 10 hours a day, we also require x1 to be less than or equal than 10. Similarly, x2 and x3 are also less than or equal than 10. Although we didn't mention it here, the number of hours have to be a non-negative number, and therefore we also ask x1, x2, and x3 to be non-negative. Since all the functions involved in this optimization model is linear, we call this model a linear program. The modeling power of linear program is extremely powerful. Many real-life problems can be solved by solving a linear program. In the optimization community, there are two kinds of researchers. The first one is those who build a model like the one we did here. The key problem is how to build a model with less variables and constraints. A naive model may contain billions of variables in practice, but a smart researcher may bring this number down to something less than 100, so there's a dramatic reduction. The second kind of researcher is those who design algorithms to solve the model. And people are trying to find faster and faster algorithms. For example, in financial industry, if you are able to solve the problem slightly faster than your competitor, then you are making a lot of profits. Let's summarize some key ingredients in constructing a mathematical program. The first thing you have to do is to identify what is your decision variables. In our previous example, the decision variables are how long the painter works each day. The second ingredient is the objective function. In our example, we would like to minimize the cost that we paid to the painter. The last ingredient is the constraints. You should be able to derive the constraints from the given story, and you should be careful about some hidden information, like the number of hours is always non-negative. When you are building a model, the first thing you have to do is to identify the decision variables. If you have identified the decision variables correctly, the objective function and the constraints should follow easily. If you find it very difficult to write down the objective function or constraints, then most likely you have defined your decision variables incorrectly. There are a few more examples in the textbook. You can easily read them and get a better feeling about a linear optimization model.